since the pandemic, I think we've all given up any hope of remaining anonymous online, because there are video.
So shall we start? Yeah, okay, I see. So good afternoon for everybody who is connected here. First, I will introduce myself as a moderator of this invited session. I am Audrius Dubietis from Laser Research Center at Vilnius University. And it's my pleasure to introduce Professor John Dudley from University of Bourgogne-Franche-Comté from France. And maybe many of us know him by his outstanding research in ultrafast optics, and in particular by his contributions in nonlinear optics in photonic crystal fibers. But he also is a quite famous lecturer, also popularizing the science and finding very interesting connections. And so I think which are, let's say, topic of his talk today. And so maybe now I will give this virtual podium to Professor. So please, we are happy to have you here. And so please take your podium.
Okay, look, thank you very much for the invitation. Thanks to all the student organizers for the excellent communication to make sure that everything is run smoothly. It's a real pleasure to see such a great team working to make a conference a success. Hopefully now you can all see my screen. If someone could just confirm that before I continue.
Yeah, we can see you.
Okay, so that's fantastic. So this is a talk which isn't really about research, or not really about my research in particular, although it touches on some of the topics. It's a general talk which just discusses some aspects of how we do research that many people, especially young students starting out, don't realize. One of the advantages of being a little bit old is that you've kind of seen things develop, and many of the structures that are in place today have their origin many decades ago. So the point of this talk is just to try to explain some of this. When you start out as a student, life is simple, but as you move through, you start to realize that the ecosystem of research and how it's structured is actually quite complicated. And depending on the group and the kind of research you do, you may find yourself part of a conflict between scientists who just want to do science and the way in which science is funded, which is by agencies who increasingly tell you what to study. And so the point of this talk is just to try to equip you with some of the vocabulary in the background to understand this, so that as you move through your career, it might be of some help when you're writing proposals or talking to people or defending your basic research. So before going into some examples, which is really what this talk is about, it's important to get the definitions correct. So when I use the word basic or pure or fundamental research, what I mean is that it's driven by curiosity. The motivation is to expand knowledge of a field. And any potential value is not at all a motivation. It's open-ended, so it doesn't necessarily have a goal of any sort. And it's usually very long-term, 5, 100 or so years. Okay. In contrast, applied research is usually understood as directing towards specific goals to solve sometimes very well-defined and practical problems. There's no real intention just to increase knowledge. There's often a connection with a business or an industry need. It's usually short-term, a few weeks to solve a specific problem, maybe a few years to develop a prototype. And it can sometimes be longer term, but it's still usually directed towards a very specific objective. So this just sets the vocabulary. But right through the history of science, the point of this talk is to show that actually there's a two-way interaction between these two things that many people just don't realize. So one of the most remarkable examples that is not known anywhere near enough is that of quantum mechanics. So when we're taught quantum mechanics, depending on who's teaching you, you can start off with a very formal mathematical definition in terms of the properties of a Hilbert space and operators and so forth. And even when it's taught in a less formal way, it's still taught in a very fundamental manner, highlighting the intellectual genius of the founders of quantum theory. But in fact, the very origin of quantum mechanics came from an extraordinarily practical problem, which was when the city of Berlin in the late 1800s had to decide whether or not to change its lighting from gas to electricity. And in the same way today, when we decide whether we replace our lights with LEDs, we take particular care to measure the spectrum of the light source. And it was through industrial contracts from Siemens that the very first measurements of blackbody spectra were made. So those measurements that ultimately led Planck to the quantum hypothesis to explain the shape of the black body spectrum came originally from a very industrial contract to try to solve, to measure the spectrum of a light source. Importantly, the environment in Berlin at the time also encouraged research into fundamental questions. You had Planck, you had Einstein, Kirchhoff, and many others. So this is something I'll come back to. So even though quantum mechanics actually came from a very practical, came about by trying to solve a practical question, of course, its subsequent development was only possible because fundamental research was supported. Now, later on, of course, quantum mechanics led to all sorts of other developments. After Planck, there were many contributions from the founders of the field, Schrödinger, Bohr, and so on. But since my own field is optics, I always like to point out that the whole field of laser physics actually dates right back to Einstein's paper on the quantum theory of radiation in 1916, 1917. And the reason I stress this is because we usually associate Einstein with let's say the public usually associate Einstein with the theories of relativity, gravity and special relativity. But it took Einstein to see the possibility of stimulated emission. So the possibility that light matter interactions could yield stimulated emission, which ultimately led to the laser, was not seen by Bohr, nor by Schrödinger, nor by Heisenberg, nor by Planck. It took Einstein's intuition to see stimulated emission. And I always like to make that point because when we're studying optics and laser physics, we're building on his insight to do so. And during the 20th century, Einstein's initial conceptual genius was then developed further to develop ideas of atomic physics, optical pumping, and so forth, ultimately leading in 1953 to the development of the microwave equivalent of the laser, the maser, and then in 1960, the first optical maser, which we now call the laser. And there's many interesting stories about the development of the laser. The one which I like the most is that the idealized approach of trying to get a 4-level system working as a laser, which was the approach by Townsend Gordon, required a slightly more complicated system. And Maimann's real contribution was to be a bit more pragmatic and have a bit more of an engineering approach to it. If you don't know this history, it's well worth looking at as another example of the link between a physicist's perspective and an engineer's perspective to develop something. And of course, there are many scientists who contributed to the development of the maser and the laser. Now, the maser and the laser and their applications were rapidly, relatively speaking, recognized with Nobel Prizes. So in 1964, to Townes, Basov, and Prokhorov for the maser laser principle, Kastler for the theory and experiments in optical pumping, and Blumbergen and Schallau for applications in spectroscopy, nonlinear optics, and so forth. And it's worthwhile at this point just reminding ourselves of exactly what the Nobel Prize actually awards. So the original terms of the Nobel Prize were really focused on recognizing research that had been of great benefit to humanity. So it wasn't enough just to do some nice physics. It had to be of benefit in some way. And there are slight differences in the the wording between the different prizes, but I don't have time to go into this. But it is interesting. If you're interested in the history of the Nobel Prize, I strongly recommend that you have a look on the Nobel Prize website, where you can read so much background information. In terms of optics and light-based science and technology, there have been over 35 Nobel Prizes, more or less directly associated with the properties of light and their applications in atomic physics, or in fields like solid state physics, or in areas such as photodynamic therapy in medicine, or microscopy, or holography, or so forth. And there's a 2020, which was the 60th anniversary of the laser. SPIE asked me to write a short commentary on the anniversary and the link with the Nobel Prize, and which I did, and I put the reference down here. And the only reason I'm doing this is because there's a great poster that you can download from the website of the journal, which the graphic artists did a fantastic job of outlining all the Nobel Prizes associated with optics and photonics. It's really nice for the lab. But in fact, you can add even more Nobel Prizes to the recognition of optics and photonics if you include applications in astrophysics, such as interferometry and optical techniques in gravitational waves, spectroscopy for the detection of spectral line shifts to discover exoplanets, the use of laser stars to correct for turbulence in the atmosphere, not to mention all the photonic detectors, such as avalanche photodiodes or photomultiplier tubes used in CERN or the Super K experiments around the world. Now, this general link with cosmology, which we start to see in these slides, you might think would have, apart from instrumentation, you might think it wouldn't have that much to do with optics and photonics. But in fact, the story is remarkable. So it's worthwhile going through this example as well. Now, when we talk about lasers, we focus on the optical version, but the maser is just as interesting as a microwave amplifier, a microwave source of light. And in fact, another piece of science which generally isn't known is that the detection of the cosmic microwave background in 1965 was only possible because the maser had been invented 10 years before. Because if you are going to measure a very weak microwave signal from space, you need to be certain that the signal is coming from space and not from some electronic amplifier. So the possibility to use a traveling wave maser, a molecular-based amplifier, which is essentially quantum noise limited, really gave great confidence in these measurements, allowing Penzias, Wilson, and the others to infer that what they were seeing really was coming from space. Now, ultimately, although Penzias and Wilson did the measurements, the interpretation and the association of that microwave signal with the Big Bang was done by others, and Peebles was one of the theoreticians who got the Nobel Prize in 2019 for his work. But what I love about this story is it shows just how interlinked different areas of research are and how little we appreciate it. For example, the timeline looks something like this. In Berlin, you start to study the properties of gas lights and electric lights. You measure a black body spectrum. This leads to quantum mechanics. This leads Einstein to propose stimulated emission as an amplification mechanism. This leads to the development of the maser. This leads to the measurement of another black body spectrum, but this time the black body spectrum of the Big Bang. And this leads to a completely new vision of our place in the universe. There's no way that you can predict from measuring a gas lamp that you're going to revolutionize the theory of the universe, but this is what happened. It's easy to make these connections looking backwards, but when you're looking forwards in research, we can't do that. And the only thing we have is that historically we know that if we allow ourselves to just follow the science wherever it takes us, some discoveries will end up like this, and they'll make revolutions in science that are completely unexpected. And this is a quotation from Charles Townes relating to the laser, where his initial work was based on microwave spectroscopy. But he says, what industrialist looking for a new cutting tool, or what doctor wanting a new surgical tool, would have urged the study of microwave spectroscopy? And the whole field of quantum electronics is a textbook example of technology growing unexpectedly out of research. And that is almost opposite to this, where we have a technological question driving a new area of basic research. So this idea of technology and basic research being in conflict is a lot more complicated than you might think. Now, unfortunately, one of the most common examples of research that is really focused on solving practical problems is associated with war and the development of weaponry. And this is terrible, but historically it's important to understand, because it's as a result of the Manhattan Project in 1945 to develop the atomic weapons that were used on Japan, that essentially all of the current model of research funding and organization is based. So after the success of the Manhattan Project, virtually the next day, the New York Times ran an editorial criticizing the normal way that universities organize research, and saying that when the research was conducted on behalf of the army, it was possible to obtain in 3 years, which it would have taken perhaps 50 years to develop if you relied on prima donna research scientists who work alone. And so there was a very clear sense, even in 1945, that scientists could not be trusted to decide what scientific problems they needed to work on, that it was better if they were told and if that was organized for them along military lines. Luckily, one of the most important people that you've probably never heard of, a scientist called Vannevar Bush, prevented that from happening. So he was the initial manager of the Manhattan Project. He was a visionary scientist. It was he who coined the word bit for information. He supervised Claude Shannon on an early project when Shannon was a student. And he ran and put into place all the organizational elements that allowed the science of the atomic bomb to be developed. He recognized that it was important to strike a balance between giving scientists freedom to do what they wanted and to make sure that the science led to practical applications when the science could potentially deliver one. And he came up with a linear idea of how basic research drives applied research, drives development, and drives production. So this idea of science driving technology was first written down by Bush in 1945. And this is the model that has driven most of research ever since. Now, this is a little bit simplistic because it doesn't really describe this two-way flow of ideas that we've seen before with the development of quantum mechanics and the measurement of the Big Bang cosmic microwave background. So in the late 1990s, a political scientist who was an advisor to the US National Science Foundation, came up with another approach, which was you divide potential research into a space where on one axis you have practical research, and on another axis you have fundamental research. And you can associate these different areas with different people. So Edison was an industrialist who just wanted to make light bulbs, and he would get his staff to measure 1,000 samples of filaments to test one that worked, rather than think about the material science. Bohr was an idealist, a theorist who just wanted to understand nature. And somewhere in the middle, you have Louis Pasteur. And Pasteur is chosen as a kind of a balance between practical research and fundamental research, because he came from he was brought up in the countryside. So I work in Besancon, and he was not very far away in a town called Arbois. And it's a farming area where one of the big practical problems you have to solve is how to keep crops and food and wine and cheese comestible against spoilage and mold and disease. And so he set himself to try to solve that problem. And along the way, he developed the field of microbiology and the germ theory of disease. So Pasteur's quadrant, as it's called, is where a lot of current research is situated. So this quadrant model is well known, so it's been discussed in different articles, but it's probably better to get rid of this fourth area in which there's nothing significant and just split the potential research that we do into three types: basic research, research that is somehow inspired or directed to a goal or some use, and industry, where you actually want to make something that you sell. So the basic research could be the properties of glasses, for example. The use-inspired research could be how to make a glass that resists an abrasion or a scratch. And industry can be the making and the sale of a telephone with a touch screen that resists scratches. So there are these different kinds of research that goes on. And funding tends to look something like this. So most of the research is use-inspired. There is some funding for basic research. So in Europe, this would be the ERC. Some national funding would be a lot lower than this. And industry funding usually isn't direct, but it's often in terms of tax concessions or partnerships or something like this. So although use-inspired research might seem restrictive, given that this is where most of the funding is, there are examples where this can be beneficial to us. And so I'm now going to look at a few more examples just to show how this can arise in very unexpected ways. So this is one of my favorite stories of the history of science. It's the discovery of the Soliton wave. And this started in 1834, and it's described in different ways, but many of which are wrong. But the true story is that John Scott Russell was doing systematic experiments on a canal to discover how a boat would travel in a canal based on the shape of the hull. Okay, so he was trying to basically do experiments designing boats. And one day in his experiment, he was using horses over here to pull this way, and then the boat would go this way. And one day in the experiment, a rope somewhere in the apparatus broke. So the boat was no longer connected to the motive force provided by the horses. So the boat stopped, but he noticed that there was a wave underneath the boat that kept on going. So he popped on another horse, and then he followed it down 5 or 6 kilometers in the canal. And if you ever have the chance to visit Heriot-Watt University in Scotland near Edinburgh, near the Edinburgh airport, there's a little pilgrimage site that you have to visit where John Scott Russell did these experiments. And to give you an idea of what he saw, it's really a beautiful experiment. This is an example from a wave tank. So I hope this will work. Showing how by setting into place a water displacement, you can create a wave that will propagate essentially without changing its form, without spreading out as waves usually do, over a very, very large distance. Now, this soliton wave attracted some attention. So in France, a scientist, Henri Besancon, worked to reproduce it, and many scientists tried to model it. But it took 60 years of work before that observation of a soliton wave was understood. That's a long time. And it took that long simply because there was no theory of nonlinear partial differential equations in 1834. So it took decades to actually develop that mathematics. But eventually, two mathematicians from the Netherlands, Korteweg and de Vries, developed the theory, and they explained the shape of the wave and its propagation properties and so forth. What I like this story as well, especially when talking to students, because the solution to this problem was actually a PhD thesis by Gustav de Vries. And what's even more interesting is that when de Vries first submitted the PhD thesis, Korteweg said, no, it's not good enough, because he'd basically only done a bibliographic study repeating all the work of the others. And he said, you need to spend another year with my help, and then we'll complete the work, which he did. So for all of you who may be finishing up your PhDs and having problems convincing your supervisor that you've done enough, well, you're not alone. This is obviously a problem that's occurred for many, many years. So after de Vries and Korteweg found that solution, essentially no one really worked on nonlinear waves or nonlinear problems for 50 years. But during the Second World War, when they had developed numerical computation, both for cryptography and also to study atomic bomb implosion dynamics, Fermi, who was one of the scientists working on this, he started to wonder whether he could use the power of a computer to simulate more fundamental properties of nonlinearly coupled systems. Now, he hadn't made the connection with solitons at that time. He was just studying a different problem, which was just connecting together some springs with some nonlinear coupling and just seeing what would happen. This was purely curiosity driven. Fermi just wanted to know if a computer could solve a problem that you couldn't do by hand. So if you have 60 or 70 masses coupled together and you have some kind of force between them that is not simply a kx term, but it's a nonlinear term that allows energy exchange, he wanted to study how energy was transferred from one normal mode of the system, which you excited, into all of them, and he expected to see thermodynamic equipartition. But he saw something completely different, and in the paper they say, let us say that the results of the computations are surprising, because what he saw was that if you trace the amplitude or the energy of one mode of the system, it would fluctuate in this very unexpected way. And what he had discovered was a nonlinear coupling, and later it was shown that this is a part of a landscape of nonlinear effects that also includes effects such as chaos. So if you, in 1962, which was only 7 years after the Fermi-Pasteur-Ulam experiment, numerical experiment, Edward Lorenz discovered the strange attractor of the Lorentz equation system in atmospheric convection. And it was the extension of this work over many years towards studying disorder, complexity, and climate change, which was recognized in last year's Nobel Prize as well. So let's just think about this. We've gone from studying a wave on some water, initially motivated by trying to make a boat go faster, to modeling climate. And they all build, you can see how they are all connected in a almost linear way. Although at the time, no one would have seen this looking forward. Now, in optics, nonlinearity was also being studied in the 1960s through second harmonic generation. There's a famous story that the first paper of second harmonic generation actually removed the spot on the spectrograph for the second harmonic spot. Luckily for us, another paper actually preserved that photograph. So we do actually have the proof from the 1960s that second harmonic generation was observed. In other work going on with laser physics, 3 years after the laser was reported in 1960, we had the observation of mode locking in lasers, which is a way of making short pulses from laser light by ensuring that the phase of the cavity modes between the mirrors remains constant and doesn't evolve in some kind of random way. And when you do this, you can see quite easily that you're going to generate short pulses of light when the different frequencies of the laser overlap constructively, and you'll generate destructive interference in between these short pulses. So this gives rise to localizing the energy of light into short pulses that can be used for applications, although at the time this was done, no one knew really what the applications would be. One area of research which was not really considered to be an application, but more of a problem, was the fact that when you focused one of these pulsed lasers with high energy into a material, just like a piece of glass, the glass would damage the material. It would create a filament where the structure of the glass would be permanently deformed. And what was interesting about this was that Charles Townes himself realized that this actually implied that what you were seeing was a kind of a soliton effect, because normally light should spread when you focus it through diffraction, but he recognized that you could nonlinearly change the refractive index of the material, leading to a self-focusing effect, and these two phenomena could compensate themselves and form an optical spatial version of the soliton wave. Also in the 1960s, since pulsed lasers were available, other scientists were thinking of real applications. So Charles Cowell worked on the very real possibility of using modulated lasers to encode information in a telecommunications context. So Charles Cowell was interested in sending signals through optical fiber. This is the Google Doodle from the 4th of November last year, celebrating what would have been his 88th birthday, I believe. And what's interesting just in passing about this is that it's quite a detailed picture. It includes reflection at the boundaries. And if you translate this binary sequence into ASCII, and then you translate to the letter codes, you actually get his name, KAO, which is a really, really nice. But this just shows how research was evolving using lasers, now looking for communications. And for many years, people started to wonder, what's the best way to use lasers for information transfer in an optical fiber? So in the 1980s, in Bell Labs, they realized that you could actually make a temporal equivalent of the soliton wave that had been seen in water waves and in spatial focusing, where dispersion in the fiber and self-phase modulation could balance each other to essentially make a pulse that would be invariant. And so this was a wonderful ideal. If you had a pulse which wouldn't distort, then maybe you could use that pulse as your one bit, where you can always send that can be the carrier of your information. Now, as it turns out, although a lot of theory was carried out and thousands of papers from scientists all around the world studying temporal solitons, solitons and optical fibers have never really found a practical application in telecommunications, even though this was what the motivation was. Okay. However, scientists building short pulse lasers started to see some unexpected behavior where the bandwidth of the pulse in the laser was often broader than the bandwidth of the gain medium inside the laser dye or the laser crystal. And it turned out that very quickly, again from Bell Labs, that they had actually created a soliton inside a laser. So the pulse formation mechanism between the dispersion of the different elements in the laser and the self-phase modulation, because the light was focused into a gain medium, that was essentially creating a soliton effect. And all that theory, which never really found an application in making a soliton telecom system commercially that worked, could be essentially instantly transferred to laser design. And it gets even better than that, because in the 1990s, when the titanium sapphire laser was discovered serendipitously in St Andrews in Scotland, and also in Bell Labs and elsewhere, they realized that there were two soliton-like effects going on inside the laser. One in the time domain, and that was the contribution from Wilson Sibbett, and another in the spatial domain, and that was the contribution from Ursula Keller and Wayne Knox. And essentially what's going on, for those of you who do ultrafast lasers, what's going on is that you have a kind of a dispersion management process which determines the temporal properties of your pulse. But the reason the laser works in the first place in a pulsed mode and not a continuous mode is because you have a diffraction, or a kind of a weak nonlinear diffraction effect when the laser is operating in the pulsed regime, that allows you to discriminate or differentiate between the two different operating modes. Now, optimizing these lasers required soliton physics, which came from the fundamental research first of all, the telecom research. It was all combined, and it allowed us to study optimizing these solitary lasers. And then when it became possible to construct optical fiber that had zero dispersion or anomalous dispersion near the operating regimes of these titanium sapphire lasers, it was possible to generate a supercontinuum. And understanding that supercontinuum and its stability required, again, that all the theory of soliton physics and soliton coherence was transferred into a new field. And this led to the development of the stabilized frequency cone and another Nobel Prize in 2005 to Hall and Hansch. And Glauber got half of the prize for the quantum theory of coherence, which predated all this. Now, if that wasn't enough, as an example of this bizarre way that fundamental things and applied things link together, then you end up with another application. Because one of the problems that had been noted, even in the 1980s with the early generation of ultrafast pulses, was that if you try to amplify the energy of an ultra short laser pulse, then the energy of the pulse can actually damage the material through self-focusing. So the very phenomenon seen in 1965 that led to the ideas of filamentation and spatial solitons was damaging the development of and impeding the development of high power lasers. And so this is where Gerard Mourou and Donna Strickland at Rochester had the idea of taking a solution from the military and civil applications of radar, which avoided the electronic blow-up of amplifying radar signals, by stretching the pulse through the introduction of a frequency chirp to keep the energy same but reducing the power, the peak power, then amplifying it, and then recompressing it to get that very high power that you want to achieve. Going from this step to this step would be impossible without blowing up your amplifying medium, but by stretching and compressing the pulse, you can do it. And this led to the 2018 prize for Nobel Prize for Strickland and Mourou. And the applications of chirp pulse amplification for high power lasers are, again, in unexpected areas. Clean micromachining of medical devices. If you've got members of your family who may have stents to keep the arteries open to prevent heart attacks, these will have been micromachined in many cases by femtosecond lasers, correcting vision problems, or more exotic but extremely important solutions of using lasers to remove orbital debris in the field of satellites. And this really is, again, just another example of practical applications coming out of a combination of fundamental and applied research. And this occurs everywhere. So if you go back to the Nobel Prize, okay, the Nobel Prizes are awarded for research that has had benefit. And so it's increasingly common to see awards for basic research that has really had a societal application. Now, this has always been the case. So you go back to the 1950s, and the Nobel Prize was awarded for essentially for the discovery of the transistor. Okay, and without the transistor, we wouldn't have modern electronics. 20 years ago, the Nobel Prize went for the integrated circuit, which is at the heart of every CPU, and the development of optoelectronic devices, the double heterostructure for high-speed optoelectronic modulation, which underpins information transfer. So more recently, 2007, Albert Fehr and Grunberg won the Nobel Prize for the development of giant magnetoresistance, which led to the compact hard drive. Now, most of the audience may not remember the revolution that occurred in the mid-2000s with the availability of the iPod, which really brought a small hard drive into a very compact footprint that you could put inside your pocket. These days we have different sources of memory, and it's not beyond imagination that something like the physics of the solid state memory, the SSD, could also be recognized by a Nobel Prize at some point. Okay, so this is the kind of thing. In 2009, optical fiber communications, as well as the CCD sensor, got recognized by the Nobel Prize. And in 2014, the basic research underpinning the blue LED, which has basically given us all flat screens and telephones and color in our computer life, and energy efficiency in lighting, was also recognized. So the Nobel Prize is implicitly recognizing this mix between basic and applied research. And perhaps one of the other areas in a different field other than physics, which is probably even more important, is the battery, because without the chemistry underpinning the battery, then, which was recognized by the Nobel Prize 2019, we wouldn't have any of these mobile electronics, and millions of people around the world would very simply not be alive today because they've been kept alive by pacemakers, and many people who have hearing problems wouldn't be able to hear because there'd be no compact batteries in their hearing assisting devices. So when we think about research, we need to be aware that this basic research can have applications, sometimes in unexpected directions, and sometimes a long time from when the discoveries were made. Now, I'm just going to conclude with 3 or 4 more slides for some food for thought, and which might lead us into some questions. So this is a slide from Ted Hans, which he showed in his Nobel Prize lecture in 2005, where he asked the question, essentially, is the current environment of funding goal-oriented research essentially constraining ourselves too much, because we might be putting ourselves behind bars where, in fact, the easiest way to get to the solution would be to walk around them and just to find them. Okay, good question. And it's a nice picture. And this has really got me worried because, especially for young researchers, I really wonder today if you are seeing the best way to do research, because more and more today, even basic research is only funded if the goals are defined. So even with something like the ERC, there's still very often the expectation that your research proposal is project managed in a very precise way, and it's based on really testing hypotheses that solve difficult questions, but which introduce new concepts. So the funding is being given for the new conceptual approach, but you're still trying to solve a very, very well-defined problem. So you're directing towards a goal, and the so-called fishing expeditions are negatively viewed. So just research to try things out is a bad thing, and it's hardly ever funded. And this is a great quote from a very famous solid-state physicist. If you've ever done solid-state physics, you will have read his book, where he says, I'm waiting for the day when people remember the fact that discovery doesn't work by deciding what you want and then discovering it. And more, hypothesis-driven research is essentially this. And I think what we're losing is the ability to play with science. And this is a quote from Feynman in 1946, where he was a bit depressed after the Second World War. His wife had just died. He had a permanent position in Cornell, but he was depressed and unable to work. And he said, now that I'm burned out, I'm just going to have fun with physics, and I'm not going to worry about why it's important. And then he was just watching someone throw a plate in the air in a cafeteria, and he started to work out the motion of the rotating plate, first of all using Lagrangian techniques, then using Newtonian methods to try to understand how it worked. But what he says is that at the time, this was absolutely unimportant. But ultimately, the things he started to think about led to the Feynman diagrams, led to the idea of minimization techniques and path integrals in quantum mechanics, and his alternative theory for quantum electrodynamics based on Feynman diagrams. So this is the conclusion of the talk. It's been a little bit disjointed in places, showing how fundamental and applied research coexist, but that's deliberate because the way in which they have coexisted has always been hard to predict. But what we do know is that there have always been unexpected connections of tremendous benefit providing that scientists have had the time to follow up unexpected leads. And maybe this is some advice. I don't think we'll change the funding system. Of course, I think we should always try, and we should know these stories to tell the funding agencies and remind them of the fact that they should support basic science. But even while we can't change the system, what we can do to some extent is to try to leave time for ourselves just to play with things. And so what I've tried to do, and what I think many scientists try to do in their careers, is to try to reserve at least some time and try to keep some of the funding that you get in a little pot or in some way that you can use just to follow up unexpected directions. And I think that is some practical advice, especially for the younger researchers, just not to constrain yourself behind the bars of the goals of what your research project may be telling you have to spend your time on. Keep time for yourself, trust your instincts, and if there's unexpected directions, follow them up, at least for a while, to see where they lead, because you never know, it might be that particular discovery which really opens up something new for science and for your careers. So on that, I'll just stop, and I'm looking forward to some questions.
Okay, thank you so much for such exciting presentation. And yes, now we have some small time left for a few questions. So just how to see if anyone raises the hand or. So I see okay, I do not see questions, but maybe I will start with a question. So your last, let's say, the last line in your, let's say, main points is that just try to reserve some, at least 20% for, let's say, to follow the up directions, which is just not for goal driven, but for physics. Okay, what is your opinion about, because okay, we have all, let's say, all of us scientists are, let's say, on this project-based research, which is actually asks you to, let's say, to have some point which are you trying to achieve, and so there is nothing left for a fantasy. And also there is another, let's say, bad thing, or just which is increasing, is the bureaucracy. So, and this bureaucracy is actually killing this 20% of which can be devoted to physics. What are you thinking about? What is your experience?
Look, I think well, I think so this system and these problems with the system will not be changed by us. It will be changed by the young students who are listening. So as you young people move into your academic systems, you will be exposed to this. And I think that you can fight it with energy that we don't have anymore. We're tired, we're worn out by these fights. We've tried and we failed. But young people, you have the energy, if you organize yourselves, to change things. And so as you move through your careers, one of the things I wanted to point out was that what the problems are and what you can change. Okay, now the leading nothing to fantasy is a great expression, and I think I'm going to remember that because it's so true. I just think I don't think that we should be as concerned about meeting our project deliverables as we usually are. So I've been to lots of project meetings, and I see colleagues, especially younger researchers, who are terrified not to meet the deliverables of the project. And I actually think that you only really have to meet about 80% of them. And providing you do other good things, the project officer may be a bit unhappy, but they're not going to turn the tap off. providing it's not a critical deliverable that leads to other things. So I think we should have a bit more courage to defend what we do. Now, different systems are different. It's not always possible, but I think at least we should try to do this. Now, in terms of the 20% of time, this is a number which I've actually taken from Google's early days, where Google used to give to all of their employees 20% time to play with information technology. And it was out of the 20% time that YouTube was developed, Google Maps was developed, and the Google ad policy was developed. Google was initially a search engine. And so its employees were basically told to optimize search, but they were told to spend 20% of their time on other things. And using this example of Google actually gets funders' attention. So in terms of 20% of the money, what we tried to do, and it has been successful in France, and different countries can be different, but we tried to get as much of the overheads back to the research group as possible. And that the overheads which we are able to keep in the research group, they can be used sometimes, not always. Sometimes they have to be used on the main project, but sometimes it's possible to share them with more fundamental research. Now, in terms of the bureaucracy, yes, well, you know, that's a terrible burden on all of us, because we are faced with I mean, I have a personal feeling that every time you open up an Excel file, it interferes with your creative process in your brain somehow, because it just seems to just destroy the nonlinear thinking, if you like, because you just have to focus on budget. And I don't have a solution to that at all. But again, if the young people can fight against that, then that would be wonderful.
Yeah, okay, sounds encouraging. Okay, are there any questions from auditorium? I do not see, or maybe just I cannot see. Someone sees any hand or whatever.
And my experience with this talk is that there aren't usually that many questions live, but I get lots of questions afterwards, and I'm perfectly happy to make these slides available to anyone who just asks. If you send me an email, I'm happy to share the slides so that you can use them yourself in your own institutes, or talking to people about how to organize your research.
Yeah, it would be great.
So I'm not sure if this is a depressing message, but I don't think so. I think it's optimistic, actually. So,
yeah.
Right, no matter what you're doing with your PhDs, keep your eyes open to fundamentally new things. And occasionally, if you do this over a career, you will really find something.
Yeah, okay. Thank you. Thank you so much. So for your very, very interesting talk. Thank you once again. And we were very happy to have you here. And
it was my pleasure.
Yeah, okay, thank you.
Okay, so thank you. I will just turn off my camera and wish you well for the rest of the conference.
Yeah, bye-bye.
Bye-bye.